Okay, so let me start by saying today we're gonna tackle one tutorial in the first session that has a little bit of both, a little bit of everything from this morning. Works with collective variables and calculates free energy in different ways. Uses what is called these geometric methods, not the alchemical methods, but I want to go back to the website that has all the tutorials here. And if you scroll down, you can see that there is a section labeled free energy and enhanced sampling methods. So basically everything in this section of the page is related to what we saw today in the morning. Okay, so we have binding free energies from alchemical and geometrical transformations. I will go today with this tutorial, what is called methods for calculating potential spin force, because I think it's a simple enough system we're gonna see, and then it gives you some the tasks are basically calculate the PMF, the potential mean force of the free energy, using SMD, ABF, or adaptive biasing forces, and umbrella sampling. So you have like three different flavors, three different options to calculate the same quantity. Okay. So if you want to follow along, please download the files here and the PDF for the instructions. Okay. So while I wait for the rest, I have here loaded the system in my computer. I'm gonna decorate it a little bit so that it looks nice. So tomorrow I'm gonna give a demo how to do advanced visualization in BMD. So for those of you who are familiar with this program, maybe that will be like the next step to do nicer images for your papers, for your cover pages, or for your posters. So for those of you that are new to BMD, this session is going to be recorded. So if you don't understand everything, that's fine. You can come back and look at this in more detail with enough time. So I'm gonna go. So what I want to do is just, as I said, while we wait, I'm gonna hide the water and the lipids. I'm gonna use something like let's say Greece. And
I have a problem, Mariano. We cannot hear you suddenly. The last like 10 seconds, 20 seconds, something happened to the microphone.
Okay, can you hear me now?
You are facing the other way around, so just.
Oh, okay, yeah, that makes sense. Let me use my yeah, I forgot to use my
No, you're very good at. Okay, thanks.
See now. Is it better now?
Yes, much better, yes.
Okay. All right, so I'm wanna show the protein with new ribbons. Okay. Yeah, I know. Okay, so let's go to the tutorial PDF, and I can maybe this. Okay, so let's switch. Let's jump to the second section, exploring this pathway with SMD. Oh wait, so I wanted to say something about the system. Yeah, let's go back to the introduction. So this is a typical problem that you may come by where you want to explore thermodynamics of this of a question using free energy. In this case, let me go back to this protein. And what is the rest username of the substrate? Let's see. So what is happening here is this is a channel. Basically, if we look at this protein from the top, we see that it has kind of like these loops form a pore where some substrates can go across the membrane. So basically, this is a membrane protein. And what we want to do in this research, let's say we're thinking about, we have this protein, we know it's a channel, so we want to quantify the free energy or the work required to, let's say, for example, make so that the substrate goes through the membrane. Okay. So we are going to do this in several different methods. As I said, but what I wanted to show here is the substrate. The substrate is I think is this one. Yeah. So this is the substrate, which is ammonia. Okay, you can see it here, and it's located right in the pore in the pore of the channel. Okay. So what we're gonna do is we are gonna in the first part, which is SMD, if you remind earlier the talk today, SMD, what it does is basically we apply an external force to move one part of the system. In this case, it's going to be the ammonia. So we're going to move the ammonia through the axis of the pore, right? In this case, it's the Z axis. You can see here in the axis of the BMD. So we're going to move this in a linear direction through the set, and for each point we're gonna compute the work associated with this movement, and we are gonna do that with, as I said at the beginning, with three different methods: SMD, namely SMD, ABF, and umbrella sampling. Okay. So this is a very simple example of a free energy calculation. The dimensions is very simple. It's only one dimension. Okay, it's gonna be through the set dimension. And okay, so now we can switch to the second part here. And this is gonna be a little bit more hands-on because the idea of this tutorial is that to show that you can do this, all these methods in NAMD and basically once you understand how to run a simulation in NumD, adding these extra methods or advanced methods is not very difficult. So if you look, let's see. Let's go over this tutorial. So the first thing it says is we need an equilibrated system as a starting point. That's important. And then the addition to run SMD is only these few lines in the configuration file. Okay, so basically these are flags that we're letting NumD know that we are running SMD. SMD is on, and then some of the extra flags are being explained here. But basically, what I'm trying to convey is that this is very simple. We are just gonna add these 6 lines to the configuration file compared to the calibration simulation, and that will give us set up the simulation for SMD. Okay, so one of the keywords here is, for example, the force constant here of the external force that you're applying, the velocity that you want this movement to go. In this case, we are pulling as the constant velocity, and then this is the direction of the pulling, which is in this case is very simple because we are only interested in the set direction. So it goes -1. And this is the frequency of the results that we want to output. And basically, this is SMD file is the reference file that contains the identity of the atoms that we want to pull. Okay, now that we are not pulling everything in our system, we are pulling like only the ammonia. So we have to flag all these atoms that are being pulled in this file. So you can see here that it explains that this file, which is named SMD01ref, is almost identical to the PDB. And it has, the main difference is that the act of flagging these atoms that are being pulled is done by adding a value in the occupancy column. Let's go to let's see this file actually. Here. Okay. So I'm here in the folder, and I'm gonna go to the SMD, and where is it here? So we're gonna look at this file, the ref file, and you can see that. Okay, so this is exactly like the PDB. Remember, this system, the PDB contained a membrane, so these are all the lipids of the membrane, a protein, and also the ammonia. So if you remember the structure of the PDB, it contains some information about the atom, the atom that is being displayed here, the residue, and the coordinates here, the X, Y, and Z, and then these are the occupancy and beta columns. So basically, this file is gonna tell NumD that the atoms that we want to pull are those that has a 1 in the occupancy column. So we can look for that if we search for example, I'm gonna search for 1, 0, 0, space here. So if I search for this in this file, the only occurrence of this 1 in this column is actually the nitrogen of the ammonia. Okay. Yeah. So that's how we tell NumD again that this is the atom, or if we were pulling more than 1 atom, for example, we will flag all of these atoms with a 1. Okay. Go back. Okay. So again, these are the simple lines that you need to add to run SMD. And this is a very simple case because again, the direction of the pulling is pretty straightforward, so we don't need to make any complicated things. So another thing that is present in this simulation, if you think about it, So when we pull this ammonia, we are trying to we are exerting an external force into this atom, not into the system, the rest of the atom of the system. But what could happen is that by means of this external force on ammonia, we could pull also, or ammonia could drive the protein, and that's not what we want. We want the protein to be constrained or restrained in space, and we only want the ammonia to move. So for that we use what do you call it, restrained, but the keyword is constrained. So basically we apply an external force into the atoms that we want to remain in the same place. Okay, it's like a harmonic potential to those atoms, and that is done by this sort of series of keywords. Okay, so we are basically constraining the set, and we are putting on the set coordinates. So basically, we are not allowing the protein to move in the set dimension. Okay, in the set direction. So this is like a complementary thing that you need to do, because again, if you pull this any type of atom and you don't want, and that could result in the environment to be also dry, you don't want that, so we are going to constrain the protein. There is one way of constraining. Okay, so let's keep going. Another way of constraining, in this case, keeping in place this protein, is by using Colbars. So there are two, you can think of, there are two ways to do this. We're gonna explain a little bit why Colbars can be used for constraints. And then in the next subsection of this tutorial, we're gonna use Colbars to actually drive the ammonia, push the ammonia. So as we heard earlier today, Colbars is a very powerful toolkit that is implemented in NAMD and BMD. And by using Colbars, you can basically drive your simulation to kind of like almost any non-equilibrium process that you may be interested in. So in this case, it's a very simple, let me zoom in a little bit here. Okay, this is a very simple Colbar.
There seems to be a question, Mariano.
Yes.
There is a question, I think.
Yeah, Delara, can you, yeah, go ahead.
Hello, thanks. Do you hear me?
Yes.
Yes. Would you please explain a bit about that occupancy in the PDB file?
Yeah, it's just the column is called occupancy. It's just a label that we gave to that column in the PDB. So it's just that if you, yeah.
When we change this, I know that sometimes in simulation, for example, they put 1 there or 0. I want to mean physically, what's the meaning when we put?
There is no meaning physically.
Number?
It's just that
what
it's
happens?
a label. It's just a label. It's a property of that line. So that line in the PDB is an atom that has some properties like the coordinates X, Y, and Z, and that's just another property. It doesn't have any physical meaning.
Yeah, if I might interject,
okay.
Mariano is right. It doesn't have any physical meaning for the simulations, but it has meaning in crystallography. So how much density you can see there? Is it 100%? Is it 50% or whatever? They put the number there, but we don't use it at all for simulations. So we can use that spot to flag an atom for various reasons. Yeah.
Yeah, thanks.
Thanks a lot. And excuse me, another question is that when we want to pull the ammonia toward through the channel, this force is exerted on the whole molecule or on the, for example, one of its atoms?
Actually, we saw that in the file. The only atom from ammonia that has the 1 in the column was the nitrogen. So that means that only in the nitrogen is the force being exerted, because the light atoms of hydrogen atoms are very light, so they follow whatever happens. They are bound to nitrogen, so they follow nitrogen. Okay. Yeah.
Okay, and that force cannot have an effect on the bonds between oxygen and the hydrogen. It doesn't change anything on that bond.
No, because remember that we are having a force field. So the force field that is defining all the connections, all the bonds, angles, and the heteros is much stronger than any external force that we are applying. Yeah.
Okay. Thanks a lot. Thanks.
No problem. So yeah, that's a good point, because sometimes you want to be clever in the way you select which atoms are being pulled. You use the heavy atoms of the entity, the molecule that I want to pull. Okay, so let's go back to this part, which is the collective variables. So let me explain. I think Jerome did a great job showing examples of collective variables. So let me just briefly go over what this collective variable does. And as I said earlier, this is a collective variable that it only has basically, it defines a distance between the atoms. Let's see, I'm okay with this. Or did I switch to the? Yeah. Okay. So this is the file called restrain.in. So we can see it here. And what it has is it has a definition of a collective variable named restrain01. And this information here, the lower boundary and the upper boundary, basically tells you that you are restraining your collective variable between 0 and 8. Okay, and basically you are applying a force constant, basically a harmonic, to that collective variable, so that it keeps the collective variable between the values that you keep. So basically, again, this is a restraint, and the way you restrain a collective variable is by adding these keywords, lower boundary and upper boundary, and the constant associated to those walls. And so what is actually the collective variable? The collective variable is a distance between the ammonia atoms, okay, and the protein atoms. And we are interested in a particular distance, which is the distance that is projected in the z-axis. Okay. And in order to do that, we need to add this keyword that is basically telling you, okay, this is a distance, but I'm only interested in the distance in this particular axis. Okay. So again, this is the definition of a distance between the ammonia and the protein. And when you add this, something that I think Jerome explained, but I want to go over it anyway. So when you add several atoms here in the atom number, so for example, here I'm listing the protein atoms, what it does is basically takes the center of mass of such atoms, okay? So if I write all the atoms of the protein, the distance that I'm calculating in this callbar is actually the center of mass, the distance between the center of mass of the protein and the center of mass of the other group, okay, which in this case is the ammonia. Okay. Okay, so then you can run the simulation, and let me see. We're not gonna go over this part of the analysis, but you can do that, and we're gonna skip this part, and we're gonna go directly to the results. Okay, so here we see that these are the plots that you generate in the tutorial, and here we see the system again, the ammonia going through the protein, and basically this is the result of the converged result of the free energy in these units of dragging the ammonia along the Z axis. This is the channel position. This is like the coordinates along the Z axis. And we see that it goes, so at 0, which is, I would assume is like in the middle of the top of the protein, it has a large peak. So that's like the most difficult part to go through, and then it goes down. And okay. But again, this is one of the methods that you can do to calculate the free energy, and it's a little bit of I would say it's a little bit of brute force. You're brute forcing your molecule through this by pushing it with a constant velocity, applying an external force, and depending on the system that you have, that might result in some instabilities. You may be disturbing too much your system, and that it's not. That's why SMD is kind of like, it's a good preliminary analysis, but it's not. There are better methods to get more accurate results. Okay, so up until this point, is there any question here?
Yes.
Yeah, go ahead.
Can you hear me? Okay, so I had a question along, and in the setup, I have a couple questions. So,
yes.
You know, here in the setup, it actually recommends that when you're like pulling, you're setting the velocity for your substrate through your channel in this case, that you set it just as low as possible. So I'm wondering, is that something that also will be affected by like the scenario you're trying to model? So like, let's say you have, you know, a membrane across two different osmotic concentrations, right? And you have a differential in force acting there. Would you change that through the velocity, like trying to solve for, you know, the effective velocity by finding that osmotic pressure difference? Or is there a different parameter for kind of setting that parameter? Do you understand what I'm trying to ask? Like the scenario
I
model.
think so, yeah. So I would say that the velocity you use in SMD, so the pooling, doesn't really, so the results should not depend on the velocity that you use. So in principle, what you need to do is you need to sample enough along that direction so that the results are converged. So I think what you're trying to say is that if you have a difference in concentration that makes the substrate go through the channel, you don't need to mimic the natural velocity of that substrate. Or in other words, you don't need to try to mimic that force that the substrate would experience due to this concentration gradient. Okay, and remember, this is kind of like a non-equilibrium phenomenon. So it doesn't relate to what will be an equilibrium phenomenon, which is like the going through the membrane because you have a different gradient, concentration gradient. Okay, does that make sense?
Yeah, can I actually ask a follow-up question?
Yeah.
So maybe I should, you know, preface by actually saying what I'm trying to achieve, which is trying to calculate the kinetics of transport across, you know, this channel. And so initially I was thinking that, okay, you use this mean force method to calculate like a delta G. And from that delta G, you can calculate the kinetics in one direction, right?
Mm-hmm.
Is that the kind of preferred mate instead of kind of going away the, no?
No. No, I would say that when you're interested in kinetics, you need to do, I mean, you can get an approximation from the free energy but I would say you need to use some way of computing the I'm missing this word.
The diffusion constant. You
The
need
diffusion constant. Yeah.
Right.
So
Yeah, I mean, yeah. So you can't get kinetic if you are pushing things around. This is a trick just to get the thermodynamic of the process, and then you have to bring in, as Mariano pointed out, some estimate of the diffusion constant and use something like a Smoluchowski's equation to get the kinetic of this process. From this type of calculation, you cannot get any kinetic information, actually.
Okay. Okay.
So in your case, if you're interested in something that like it's in a spontaneous process that occurs with a concentration gradient, then I would probably tackle this problem by first generating this concentration gradient in my system. Sometimes it's not possible. Sometimes you need too many. Usually, concentration is a very difficult thing to mimic. But if you can do that, maybe by using some different type of external forces, like grid forces, for example, then maybe if you mimic that external potential, then the process that you see, if you run just equilibrium simulation with those grid forces, hopefully you will see that process going, your substrate going through the membrane. Does it make sense?
Yeah.
And then if you run those simulations long enough and you have enough sampling, then you can compute the diffusion coefficient from that simulation, which is not it's not a non-equilibrium simulation. It's an equilibrium simulation by means of a concentration gradient, but it's a little bit tricky. Yeah.
Okay. And then I do have one more question.
Yeah, go ahead.
So when we're defining a system, so far it looks like we're just using this plain text file in order to set the parameters. Is there any tools for using the GUI to kind of illustrate and define how, like, the vector that is acting on this particle, and kind of utilize kind of to understand, like, okay, I've set this text file, but maybe I have my axis wrong. Is there any way of using the GUI to kind of graphically illustrate this is where your vector is, so that way you know that you're pointing in the right direction, you've got the right magnitude?
I would say that probably let's continue a little bit more, because the next section is going to show you how to use the collective variable module to actually drive your non-equilibrium simulation, which is a little bit more powerful than just the SMD. So if you use that, then you can use the GUI that Jerome showed, the Colbar's dashboard, and that way you can basically display what your collective variable will look like and how it will look like in your simulation. Okay, but I'm not sure if there is something that it's. I mean, remember, this is one of the best things about BMD, which is the tool that we use to display everything, is that it's very customizable, and it's very scriptable. So basically, it has a everything that you see you can customize in a script. And if you're, but what you're saying is it's a little bit more complicated, and I don't think it's there in any of the tools that we have. But definitely, Colbar's dashboard, it's a good option.
Thank you.
Okay, so let's go. So the next section is the same problem by now using this adaptive biasing force, which Chris Tripod in the morning session described. And so the idea is that now we're going to use Colbar's to set up this non-equilibrium simulation. And let me jump to the here, to where the file, the Colbars file is. And now we can see that, so this is called in these folders, go back one and do ABF. And yeah, so this is one of the files called win.in. And basically, we are telling NAMD to use Colbars and to use this definition of Colbars given by this file. This file, for example, could be created by the Colbars dashboard. And the idea of this, now we have a Colbar definition and an ABF definition, which basically we are saying, okay, this is the Colbar that I defined, and now I'm applying this method for basically pushing or making my non-equilibrium simulation go. Okay, so it's very simple. So let's look at this Colbar and compare this with the other option that with the previous example of Colbars, which was just a restraint of the position of the protein. Okay, so now we are. It's very similar. I have here this file that is one of the examples, and in this file we are setting up again a boundary where this value of Colbar can be, it cannot be outside of 2 and outside of 7. Okay, and this is a wall constants. So basically, it's the same template as before. We are giving a restraint, but inside this range, it can move freely. Okay, and that's the main point. Sorry, that's the main point. ABF is kind of like a more relaxed method. It's a little bit more soft, if you want, compared to SMD, in the sense that SMD just pulls, and in ABF we allow the system to basically explore, sample along this range, in this case, which is like 5 Armstrong range, and it's gonna learn and it's gonna sample every part of that range. So again, the type of Colbar, this is a distance C, which is the distance between two groups of atoms projected into the Z axis. And here the atoms are the same. It's between ammonia atoms and protein atoms. So the center of mass of ammonia and the center of mass of the protein. Okay, and then, as I mentioned earlier, so we are using this ABF method over this Colbar called translocation. This is the name of the Colbar, and this is a keyword that is basically telling the system, telling NAMD that we need to explore and we need to have enough sample so that we sample 1,000 times along this range. Okay, so basically, the larger this value, the longer it will take for the simulation, but also it will be better in terms of convergence. Okay. Okay, so in this case, if you go back to the folder, you can see that we split the analysis into windows, and this is something that is very practical, because sometimes that speed ups the calculation in general. Because if you think about it, I'm sampling one of the. Let me go back to PMD, and this is the ammonia. So let's say I'm gonna see. So I slice my path in 4 windows, okay, and then I ask ABF to sample the ammonia around, let's say, between 2 and 7 Armstrongs of the Colbar, then between 7 and 12, and so on and so forth. And basically, all these simulations which are independent can be run at the same time, and you end up speeding up your whole calculation. Okay, because this is compared to SMD, which was like one single trajectory that I pulled from top to bottom, and I gather information about the pooling. This is a sampling method. So this is a trick. Slicing my path into different windows is a trick to get more sampling at the in parallel. Okay. So when you do that, you go back to the analysis, and the analysis, what it does is basically combines all the windows into a single sampling, and that based on the probability of each point in the sampling gives you the free energy. Okay. So for example, here we have the result of the ABF free energy of potential mean force, and we can see that it's quite different compared to the one from SMD. Okay. And what it shows here is that we can identify some of the peaks and valleys in the free energy, and then we can identify some of the nearby residues that may be interacting favorably, or for example, to lower the free energy here. Okay. Are there any questions so far?
Yeah. Hi. Hello.
Go ahead.
Okay. So what if I change the wall constant you have shown in the Cold War module for ABF to very high value?
Yes. As I think the value was 100.
Yeah.
Yes. So that value is basically giving it's a large value, because the goal is just to avoid for the Colbert to go outside of this range. Okay, this between, for example, 2 and 7. Is that okay?
So what I understand is like when we do umbrella sampling, we basically define the windows, right?
For umbrella sampling, you can also define windows. Yes.
But there actually we look into the histograms that there should be a particular overlap to define the windows.
Yes.
So how do we define the windows in this ABF?
You can in this. I mean, I would say there is no one recipe for every system. If you did umbrella sampling, you can use the same windows that you use for umbrella sampling. We're going to explain umbrella sampling in the next section, but if you use a certain amount of windows, certain splitting for your trajectory, for your path, then you can do the same. The idea is that the main difference between, we're going to cover umbrella sampling a little bit now, but the main difference between umbrella sampling and ABF is that in umbrella sampling, we usually tend to have small windows and sample them enough, and then we need to be careful that the windows overlap. Whereas in ABF, usually we have a slightly larger windows, because ABF has this parameter that is the full samples, that basically tells you continue until you sample enough all this window. Okay, and then it's gonna accommodate the biasing so that it samples whatever it is in sample. Okay, in that window. Okay.
So basically, I can confirm that the number which I'm putting here for full samples, I will be getting that number, right?
Yes.
Yeah. So 1,000 is a standard.
I don't think so. Not necessarily. Remember, these tutorials, the files that are provided or the instructions that are provided in tutorials are so that you can run them in a reasonable enough time. That doesn't mean that the numbers that we have here in the tutorials are the standards and those are the ones that you need to do to publish. Okay. I would say that one thing you can do usually in any problem is to run your simulation with different. If you have a parameter you don't know exactly what the value should be, you should run your simulation with different values of that parameter. Let's say 1,000, 5,000. Okay, and then compare the results. If your results are independent of that parameter, then you can trust that your results are correct. Does that make sense? Again, I said that this parameter in particular is just kind of like, it relates to the sampling. So the larger this parameter, the better. Okay, but I wouldn't say that this is actually the standard parameter by no means. It depends on your system. Okay.
Okay. So I have one more question regarding SMD actually.
Yes, go ahead.
So actually, in this tutorial, it has been shown that you can actually calculate the force, but not it is nowhere mentioned that like how to get the PMF from this SMD calculations.
Yeah, I didn't cover that, but it's just it's here in the tutorial. So I skipped that part because it just explains. I mean, it's just we need to follow the instructions, but yeah, it's here.
This is giving me the force.
Can I make a comment?
Yeah.
Yeah, is right. I mean, SMD will give you some force profile from an irreversible transformation. It's not going to give you the PMF right away. I mean, if you want the PMF, you can either do use an equilibrium method like ABF or like umbrella sampling. If you want to stick to SMD, then you'll have to go for the Jarzynski identity and then repeat your realization many times. In something I didn't mention this morning because I had to leave the floor for Jerome, but the problem with the Jarzynski identity is that although formally in the 1997 paper, it says that it works in general. I mean, it's in practice you need to be in a near equilibrium condition in order for your average to converge. Of course, there are tricks you can use, for instance, cumulant expansion. Basically, what you want to have is a Gaussian distribution of your work. If you have something that is, if you're pulling too fast, then you're moving away from second order perturbation theory. And so you don't have any more a Gaussian distribution. So now you can use some tricks like a cumulant expansion. But there is a limit beyond which you cannot use it. I mean, if you're really pulling too fast, it's beyond repair, and you won't be able to apply the Jarzynski identity. I mean, you'll have like too little realization for which you have a negative work, and then you will be overwhelmed by too many positive work, and your average over positive work is just going to give you crap. So again, that's the difference between theory and practice. In theory, yes, the Jarzynski identity can be used in many cases, all the cases that you can think of. In practice, you need to be in a near equilibrium condition. So don't pull too fast. And pardon me?
Yeah, that is what I wanted to ask, like if there is any plugin attached to the SMD so that we can get the PMF profile.
I didn't get the question. Is there what?
So actually, that is what I was asking, that if there is a way, like in NAMD only, that we can use that identity to get the PMF profile.
Yeah, I mean, yes, you can. I mean, you can generate these PMFs. It's just actually you can do SMD with NAMD either directly with NAMD, or you can use SMD within Colvars. It's kind of, there is almost like a little redundancy. There is directly in NAMD without Colvars, there is an SMD feature, and there is an SMD keyword and or series of keywords for SMD.
Yeah, I think what he means.
If you want to use a more elaborate collective variable and do SMD on that elaborate collective variable, then you're better off using Colvars and doing your SMD within Colvars.
Yeah, I wanted to mention that I think what you're asking is the output from SMD is just the force. So there is no direct way to get the free energy, but usually we approximate this to the free energy. As I said, this is a very preliminary tool, I would say. If you shouldn't trust free energy obtained from SMD, at least in my experience. But
I mean, let me Nitin, I'm not a big, I mean, as you might have surmised, I'm not a big fan of SMD and the Jarzynski identity. And there is a reason for that. I mean, it's interesting. I mean, conceptually, don't get me wrong, and theoretically, it's beautiful. I mean, this reconciliation of non-equilibrium work experiment and free energy, but in practice, there's a big price to pay to get your free energy profile, and in general, you can get the same result and better result actually for far less investment using equilibrium methods, either umbrella sampling or some variation of metadynamics like well-tempered metadynamics, or ABF. ABF will give you the answer, in no time.
Yeah.
Actually, there is a good paper. This work, this story of reconciliation of SMD simulation, the Jarzynski identity, and so on, can be traced back to 2003. There is a paper by Klaus Schulten and Emad and a guy named Sun-Yun Park. That's the first author in Journal of Chemical Physics. You will see that they actually do this many realizations. I mean, probably like hundreds, and trying to get the PMF. And it's not cheap. It's not cheap. Even if you pull like reasonably fast, but not crazily fast, those are still like, nanosecond long simulation or realization. And so you multiply this by, a number of realization that is reasonable for your identity to converge. And then you're talking about like 100 nanoseconds, right? And the same result can be obtained in less than 10 with ABF or with umbrella sampling.
Yes, I do it.
Yeah, I wanted to mention, I don't remember if you mentioned this, Chris, but in practice, we use SMD to seed any further advanced method like ABF or umbrella sampling. So it's like
that's true. That's true.
because,
actually, you might, for instance, there are cases where you want to use SMD, but not in the context of getting a free energy, but more like to prime a free energy calculations, or better yet, when you do like transition path sampling. So, for instance, if you do, if you run the so-called string method, we try to optimize a pathway and hopefully get the minimum free energy pathway. You need an initial guess for your string, and doing SMD is the way to proceed. So you basically pull in a privileged direction. And the result of that is you're going to use that as an initial guess for refining your pathway. Because I mean, what SMD will give you is a non-physical pathway. That I can guarantee. But it's a reasonable way of guessing what would be the correct pathway.